I'm going to talk about viscosity, which is section 9.9 through 9.10 in our book. So I will explain the basics of viscosity, how to maintain viscous flow, how to visualize viscous flow, how to use Puistoiuli's law, understanding viscous drag, understanding terminal viscosity, and the applications of viscosity to our world. So an ideal fluid will flow through a horizontal pipe without an additional force, whereas real fluids have viscosity. So viscosity is fluid friction, which goes against the movement of our fluid. The SI units is pascals per second, and the coefficient is the Greek letter eta, which looks like the N. To maintain a viscous flow, we need to have an applied force to go against our viscous force here. And our fluid pressure is our pressure times our area. And as you can see here in this graph, our pressure on this side, as seen here, is higher than this side. So our pressure is lower over on this side. That is because we need a pressure gradient to keep the fluid moving to go against our viscous force. So in ways that we see this in real life is blood pumping through our arteries and oil going through a pipeline. So we have kinetic friction versus viscous force. So our kinetic friction will slow down an object unless there is a force that is acting against the kinetic friction, which is if you were to push a heavy box to keep it moving. You need that applied force to keep it moving. So our viscous force is actually very similar, but it's with our fluid. So the viscous force is going against our fluid, which will make it slow down, and we need to have an applied force. And this applied force is the pressure difference, or the pressure gradient that I talked about, where if you have a pipe and you want to be flowing this way, this side needs to be higher than this side. So then the liquid will continue to move to the right. So visualizing our viscous flow. In a viscous flow, the center of the fluid will flow faster than the outer sides. The center will have the fastest flow, while the very outside will have our slowest flow, and the fluid that is in contact with our tube will not have any movement. Each layer will exert a viscous force on each other. So as you can see in this picture here, so our center is going the fastest, while these two outer layers here are going much slower. And then the liquid that is in contact with this surface here will not be moving. If we have no viscosity, all the fluids will be moving at the same speed as shown here. So when we do have our when we are going against a viscous force, the outer layers will be moving slower than the inner layers. So here I have some values of viscosity. We have the viscosity of liquids and gases, and the viscosity, as I said earlier, is shown in the Greek letter eta. So viscosity of both liquids and gases is temperature dependent, and we can see here with liquids, as our temperature increases, our viscosity will be decreasing. So liquids will be more viscous when the cohesive forces between the molecules are stronger, and the cohesive forces will be weaker as your temperature increases. So that is why our viscosity will be decreasing as our temperature increases. However, the viscosity of our gases will be increasing when our temperature increases. So like this, so our temperature is increasing, and our viscosity will also be increasing. And this is due to gas molecules colliding more often. So an important thing to remember with viscosity is with your blood. So a decrease in our body temperature is very dangerous for us because when the temperature decreases, the viscosity of our blood will increase, and that will slow down the blood flow. So Poiseuille's law takes an account of the viscous force when viscous liquid is flowing through a horizontal cylinder pipe. So he has the equation for our flow rate, which is shown with the letter Q. So our Q is the volume flow rate, P is our pressure difference between the two ends of the pipes, R is the inner radius, and L is the length of the pipe, and then the Greek letter eta is the viscosity of our fluid. So using Poiseuille's law, we have our flow rate equals pi, change of pressure, R fourth, and then 8 eta, and then our length. So for this one, we have a pressure drop or difference of 0.5 pascals. So pi times 0.5 pascals. And then our radius, which is 20 centimeters, and we have to convert that, so that'd be 0.20 meters. That'd be to the fourth, all over 8. And then we need our viscosity here. So I have 20 degrees Celsius the water is 20 degrees Celsius. So we come back to our chart here and we find 20 degrees Celsius, which is 1.0 times 10 to the third, or 10 to the negative third Pascal per second. So then we come back here, so that would be 1.0 times 10 to the negative third Pascal per second. And then our length, which is 1.5 meters right here. So the change of pressure over length is our pressure difference. So it'd be how much pressure is changing for that much length. And so I did the calculation here, and I got 0.21 meters cubed per second, which would be our flow rate. So that is our answer for this question. So now we have our flow speed in viscous fluid. So the flow speed in a viscous fluid is not uniform. It will be, as I said, it was faster in the middle and slower on the outside. So we will usually use the average flow for the viscous fluid. So to find the average velocity, we take our flow rate times our area, which would give us our velocity average. So, and then the average flow speed will be larger for wider pipes because there is more fluid that is closer to the center of our pipe, so it will be moving faster. So we also have viscous drag. Viscous drag is the force that a fluid will exert on an object when it's passing through it, which will slow down our object. Viscous drag will occur when the relative velocity between the object and the fluid is low enough for the fluid around the object to be laminar, which is when it basically will be flowing uniformly around the object. So for small objects, viscous drag is proportional to the velocity of the object, whereas for larger objects, viscous drag is proportional to the square of the velocity of the object. So the velocity squared comes from the turbulence that the object will cause. And so that means that our viscous drag depends on the size and shape of the object. So we have Stokes' law, which is the viscous drag on a sphere. So we have our force drag times our 6 pi eta r, or radius times our velocity here. So we have this equation. So a example of our viscous drag is if you were to drop a coin and a coffee filter in air. So our coin would fall pretty fast because there's not as much viscous drag on it, whereas our coffee filter would take longer for it to fall down. So we can compare our viscous drag to our kinetic frictional force. So with our kinetic frictional force, we have a force that is opposite of the motion of the object, and it will not strongly depend on speed. Whereas with viscous drag, we again have a force that is opposite of the motion of a fluid, and that will depend on our speed. So we can look at our terminal viscosity. I messed up here. This is terminal viscosity. Is an object's velocity that produces just the right drag force so that the net force is 0. And this will mean that an object will be falling at its terminal velocity and will have 0 acceleration. When the object moves at terminal velocity, the net force acting on it is 0. So as you can see here, this is the equation. So if the density of our object is greater than the density of our fluid, then our object will sink. And that will have a terminal velocity that is going down and a viscous drag that is going up. And then for this one, so our density of our object is less than the density of our fluid. And that would make the object rise. So on this one, the terminal velocity is upward while our viscous drag force is downward. And an example of this would be in air bubble and oil. So the last part that I have is our viscous drag in centrifugation. So this is something we did in biochem this year. So our viscous drag can be seen in centrifugation. The terminal velocity in this case is the sedimentation velocity, which is just another name for our terminal velocity. This is when small particles fall to the bottom through a liquid when spinning fast, and the particles will settle on the bottom here, so as we can see with the blood, to separate out the blood and the plasma. So the blood is more dense and will move to the bottom, whereas the plasma is less dense and will stay up towards the top. So in this lecture, we went over the basics of viscosity, how to maintain a viscous flow, how to visualize that viscous flow, and then how to use Poiseuille's law, understanding viscous drag, understanding terminal viscosity, and the applications of viscosity to the real world. So here are my references, and thank you for watching.